Hey everyone, welcome to 2024's Pi Day. This year I'll be using the geometric probability theory, Buffon's needle. Suppose we have a plate made of parallel strips, each with the same width. Then we drop a needle onto it. What's the probability that the needle crosses the boundary of two strips? Well, according to Buffon's needle problem, and we'll see why later, the probability is directly correlated to the length of the needle, width of the strip, and you guessed it, pi. We can rearrange this equation by multiplying both sides by pi over the probability to solve for pi. Let's go to me in the past and see how I found pi using Buffon's needle. So here's the setup. I have a box of toothpicks, each measuring about 2.5 inches long, and strips that are 3 inches wide. I'll be dropping 100 needles, counting how many touch the boundary of the strips, and using that ratio as the probability. From this, I'll calculate pi. I know I messed up this first line, but I had an audience, so I was a little nervous. Counting these toothpicks is going to take a while, so while past me counts out 100 toothpicks, let's go back to current me and talk a little history. On September 7th, 1707, George Buffon was born in Burgundy, France. In 1728, he started his study of mathematics at University of Angers. After his studies, he moved to Paris and became friends with other intellectuals such as Voltaire. Not only was Buffon interested in mathematics, but in biology, astronomy, and physics. In 1777, he finally described his needle problem. I think past me is done counting now. Let's go drop some needles. Alright, 100 toothpicks have been counted, and now it's time to drop. Let's pick some of these up, make sure I'm centered, and drop. Looks like we had a few stragglers that fell outside the page, so let's give them a redrop. Okay, now for the really fun part. Let's count up how many landed on the boundaries. Just kidding, I won't make you watch this. The results are in. Let's finally calculate pi. 54 landed on the boundaries, so the probability will be 54 over 100. And that means pi will be equal to 3.086. That's pretty close, but I think we can do better. Let's try 250 toothpicks. I'm not going to make you watch me count these. While past me's counting out 250 toothpicks, let's return to now and talk about why pi shows up in the probability equation. So why is pi here? Let's set up an example and set some variables so we can see. Let's call the length of the needle L and its center point location X. The needle will touch a boundary represented by the vertical axis when X is less than or equal to the length of the needle over 2. Since the needle could be on both sides, we'll add the other side as well and divide by the total length it could land in, d, to get the probability of L over d. But wait, where's pi? Past me just finished up counting, so let's go back there and drop some more toothpicks before we find out. Let's pick up the last couple and drop. Nice. Time to count again. Let's move these to the side and do some calculations. Alright, after counting, we got a ratio of 125 on 250. That's a suspiciously nice fraction, but let's continue. Time for pi 2024. 3.333, that's even worse. I guess we'll have to up the ante and do 500 toothpicks. While I get ready to drop in the past, let's talk about how that pesky pi finally shows up. Let's set up another example. Similar to before, but now instead of barely touching, the needle would go past the boundary. Before, we were only looking at the needle moving in one dimension, but in reality, the needle can rotate. Let's draw the needle like before, just barely touching, but now at an angle. We'll call this angle theta in radians, and draw the needle in the same position but mirrored on the other side. These are really the same thing statistically. I'll draw a circle around the needles to show all possible positions it could rotate in. The red area is the area where the needle would cross the boundary. We can express the angle theta as a function of x. The function that geometrically represents this is the inverse cosine. Then, because the angle that the toothpick touches the boundary is 2 times theta, we can take the integral from 0 to 1 of the ratio of this so-called red angle in the whole angular space the needle could rotate, pi. This gives us a probability of 2 over pi. Combining the probability we found before and this new one, we get a probability of 2L over pi d. Let's go back one more time and drop 500 toothpicks. Hopefully our result is better this time. I got a little lazy and assumed there were exactly 250 more toothpicks in the box. Once again, I picked up the stragglers and threw them back on. After painstakingly counting even more toothpicks, the results were finally in. I counted a ratio of 261 to 500, did the calculations, and the final pi for 2024 turned out to be 3.193. That's as close as I could have asked for. I really hope you enjoyed this celebration of pi and get inspired to do some math just for fun. Thanks.